All right, here we have section 8.5, angles of elevation and depression. So there's our main ideas: solve problems involving angles of elevation and solve problems involving angles of depression. And a new vocab over there. Angles of elevation. An angle of elevation is the angle between the line of sight, which is right there, and the horizontal, which is right there, when an observer looks upward. So you're down here in your house looking at the top of the cliff, and that's the angle of elevation. So example 1 here, the peak of Goose Bay Mountain is 400 meters higher than the end of the local airstrip. Peak rises above a point 2,025 meters from the end of the airstrip. Plane takes off from the end of the runway in the direction of the mountain at an angle that is kept constant until the peak has been cleared. The pilot wants to clear the mountain by 50 meters. What should the angle of elevation be for the takeoff to the nearest tenth of a degree? So draw a little picture over here. So all these problems are based off of triangles, so draw yourself a little triangle. So this is your horizontal distance, and then it has to clear a total height of 450 meters because the mountain is 400 plus the extra 50 to clear it by. And there's the distance from the end of the runway. And the plane's going to take off at some angle x. So from x, you have the opposite and the adjacent, which leads you to have a tangent problem. So the tangent of x is 450 over 2025. So if you work that division out, the tangent of x is about 0.22 repeating. Keeps going on forever. So bring the tangent across. X is equal to the inverse tangent of 0.22. If you work that out, you get about 12.4 degrees. So the plane has to have an angle of 12.4 degrees in order to clear the top of the mountain by 50 meters. Now you also have angles of depression, which is the angle when you look down. So here you are up at the top of the lighthouse. You have some angle you are looking down to see the top of the buoy over here. Now the nice thing about angles of depression is that they're also equal to the angle of elevation. Because if you think about it, if you're up top here looking down at someone, they have to look up at the exact same angle to see you. All right, so example 2 here, Olivia works in a lighthouse on a cliff. She observes 2 boats, sailboats due east of the lighthouse, so boat A here and boat B. The angles of depression are 33 to boat B and 57 to boat A. Find the distance between the 2 boats. So what you have here is there's actually 2 triangles here. So you've got this triangle, which is distance to boat A. To look down to A, she's looking down at 57 degrees. And now this distance here, you actually know. It's the 85 for the lighthouse plus the 110 from the cliff. So that's 195. And for boat B, you have a similar picture, except now the angle is 33 degrees. That's B. This, though, is still 195. Now both these, once again, are tangent problems because from 57 you have the opposite and the adjacent. So the tangent of 57 is 195 over A. And over here, tangent of 33 is 195 over B. So you can do this a couple ways. You can work that out as a decimal and then bring the A over and divide. But because of how the math works out, there's kind of a shortcut. If your variable is on the bottom of a fraction like this, the variable and the left-hand side actually just trade places. So I can write this as A equals 195 over the tangent 57, and B equals 195 over tan 33. So if you work 195 divided by the tangent 57 out, you will get 127 feet. And if you work this one out, you will get 300 feet. So how far boats are apart? Now these are distances from the shore. So A is 127 feet from the shore, B is 300 feet from the shore. So they are, the distance apart is the distance between these. If that's 127 and that's 100, or sorry, and that's 300, this part here from A to B is the full 300 minus the 127. So they are, would it be 173 feet apart. And that is the end of the section.